Hi guys, welcome back to my YouTube channel. In previous class, you learned about superposition theorem SPT, right? Okay, in this class, I will do one more problem on that theorem, and also I will start maximum power transfer theorem. Okay, this is a given network. Here, problem statement is find the current in the network shown in figure A using SPT superposition theorem. Okay, so here you have to find current in 1 ohm resistor. Okay, let's consider. Okay, so I1 and I2 currents through the 1 ohm resistor. So due to the voltage sources of 50 volt and 100 volt respectively. Okay, so I1 current flows through the 1 ohm resistor due to 50 volt and I2 due to 100 volt voltage source. Okay, so finally we have the total current flowing through the 1 ohm resistor, that is equals to the algebraic sum of I1 and I2, right? Okay, so first, I will consider the 50 volt voltage source. Okay, consider 50 volt voltage source and set other source equals to 0. Here other source is 100 volt. You have to remove this 100 volt by short circuiting, right? Okay, here see this figure. Here 10 ohm and 5 ohm, so these two resistors are connected in series. Okay, then it becomes 15 ohm, right? Here 4 and 2 are connected in series. Here resistance become 6 ohm. In the AB terminal 1 ohm resistance is connected. Here resistance becomes 15 ohm, right? You have to set this 100 volt voltage source equals to 0, right? Here resistance becomes 6 ohm, right? 4 plus 2. We are considering 50 volt. The conventionally current will flow from positive terminal, right? Okay, so this current, taken this current as total current IT. Okay, so that current will divide from this node, right? Okay, the current direction in 1 ohm resistor due to this 50 volt, that is from B to A, right? Okay, so that is I1 current. You have to find I1 current. So here, so first I will find the total current. Okay, so then after that, so you can apply the current divider rule to find the I1 current. So before that, first I have to find the total resistance, right? Here 50 and 1 ohm connected in parallel, right? So after that, so connected in series with 6 ohm. Here total resistance, that is equals to the 15 parallel with 1 and series with 6 ohm. Okay, so 15 into 1 divided by 15 plus 1, 16 plus 6. Okay, so total resistance 6.9375 ohm. Okay, yes, the total current here, the total voltage is 50 volt. 50 volt divided by total resistance. The 50 volt divided by total resistance is 6.9375. Then that is equals to the 7.2072 ampere. Okay. So now apply current divider rule at this point to find I1. So I1 equals to the total current into, right? So I1 equals to the total current into opposite resistor, right? Here 15 ohm is the opposite resistor, then sum of resistor. 15 divided by sum of resistor 15 plus 1. Okay, substitute here total current value 7.2072 into 15 ohm divided by 15 plus 1 is 16. Then I1 value 6.7566. Okay. Okay. Next find I2 current. Here consider 100 volt voltage source and set 15 volt voltage source to 0 by short circuiting. Okay. Here I have to consider 100 volt. Say AB terminal. Here this is 1 ohm, this is 15 ohm, this is 6 ohm. Here 15 volt goes to 0. Short circuited. Okay. Here this is 100 volt, right? So current direction in 1 ohm. Here total current will flow from the positive terminal, right? Okay, so that will divide from this node. So current direction is from A to B in 1 ohm resistor due to 100 volt, right? So here again find the total resistance. Okay, so total resistance here 6 and 1 ohm is connected in parallel, right? Okay, then this parallel combination is connected series with this 15 ohm. Okay, 6 parallel with 1 ohm and connected in series with 15 ohm. Okay, so 6 into 1 divided by 6 plus 1 plus 15. Okay, it's the total resistance. The total resistance value, that is equals to the 15.8571 ohm. Okay, the total current, so that is equals to the total voltage, that is 100 volt divided by the total resistance. So 100 volt divided by the total resistance value is 15.8571. Then that is equals to the total current 6.3063 ampere. Okay, so next we are applying current divider rule to find I2 current. So that is equals to the total current into opposite resistor, that is here opposite resistor is 6 ohm, right? Divided by sum of resistance 6 plus 1 equals to the, so 6.3063, that is total current into opposite resistor 6 divided by sum of resistance 6 plus 1 7. So that is equals to the 5.4051 ampere. Okay, so finally the total current across 1 ohm resistor, that is equals to the I1 plus I2. We have to do the algebraic sum, right? Okay, so here I1 current, so direction that is from B to A, right? That will flow from the terminal B to A. Okay, the I2 current is flow from A to B. Okay, here these two currents flowing in opposite direction. Okay, in 1 ohm resistor. Okay, we have to do the algebraic sum. Okay, here the I1 current is 6. We have to subtract these two values. Okay, 7566. Here the I2 value is 5.4051. Okay, the total current that is equals to the 1.3515 ampere. Okay, so here current is flowing through the 1 ohm resistor, that is from B to A. Okay. The next concept is the maximum power transfer theorem. Okay, it is also called as MPT. So here consider network. The input to the network is voltage source. Okay, so either it may be DC voltage source or AC. Okay, and also independent source or dependent source are both type. Okay, so here connecting load. Okay, here take some points. Here the MPT is valid for both independent source and dependent source. Okay, so the first point is MPT is valid for both independent source and dependent source. Okay, so the next point is the MPT is valid for the variable load. So you have to vary the load. Okay, so variable load. Okay, in next point, if in case load is fixed, we have to choose minimum internal resistance. Okay, here resistance or impedance ZS. Okay, you have to choose minimum internal impedance. So that will provide the maximum current flows through the load. Okay, that means maximum power dissipated across the load. Okay, so you will get the maximum power across the load, right? If in case load is fixed, okay, you have to choose minimum impedance, internal impedance, source impedance. Okay, see in fourth point is it provides almost 50% efficiency. Okay, so in this theorem, find the useful application while evaluating the impedance of the load, that will connected to the terminals. Okay, so that will connected across the terminal A and B. Okay, so that the maximum power get transferred from the network to the load. Okay, so we shall consider several different cases here. Let's start. In case 1, the fixed source resistance and variable load resistance. Okay, if in case load is purely resistive. Okay, so here you have to choose source impedance as source resistance, and load is variable load. Okay, so DC source Vs. Okay, source resistance Rs. Okay, here variable load resistor, that is RL. Here find current across RL. Okay. In this theorem, so you have to find the maximum power across this load resistor. Okay. So maximum power transferred from the source, the MPT. Okay. So here, so current flowing through this load resistor, that is IL, that must be maximum, then only you get the maximum power across this RL, right? So IL, that is equals to the, here RS and RL, so these two resistors are connected in series. The IL value, that is Vs divided by RS plus RL, right? Okay, consider this is your equation 1. Okay, the power across this load resistor, that is PL. Okay, so power across load resistor, that is equals to the IL square into RL, right? Okay, substitute this IL value here. So Vs divided by RS plus RL whole square into RL, right? Consider this equation as 2. Okay, so here you have to find not only power across the load resistor, you have to find the maximum power across the load. To get the maximum power, you have to differentiate this equation with variable element in the load. Here variable element is RL. Okay, so this is equation 2. Here you have to find maximum power, right? Okay, so here differentiating this equation 2 with respect to variable element, that is RL, right? Here differentiating the maximum value. Okay, with respect to anything, so what you get? So you get 0, right? So maximum means that is constant. So maximum value means that is constant value, right? So differentiating constant value with respect to anything, so you will get the 0 value. Okay, so here so differentiating equation 2, here denominator square, right? U divided by V formula, here applying the whole square, right? Okay, so here RS plus RL square, so differentiating numerator in term, that is VS square into RL. Here differentiating with respect to RL, so remaining VS square. Okay, so next minus, so numerator VS square into RL constant, so denominator differentiate denominators, so here 2 into RS plus RL, again differentiating RL, that is equals to 1, right? Equate to 0. Okay, here this term becomes 0, right? Cross multiplying with 0 equals to 0. So remaining, so what you get here in this equation, the constant term in these two term is, so RS plus RL, right? Here also RS plus RL and also VS square. Okay, take it outside, RS plus RL, right? And VS square. Okay, so here remaining term RS plus RL, right? Okay, here minus, so RS plus RL is taken outside and remaining 2 RL, that is equals to 0. Okay, so this whole term becomes 0, right? So remaining Rs plus RL minus 2RL equals to 0. Okay. Here Rs, here RL minus 2RL. So what you get? Minus RL equals to 0. So finally RL equals to the Rs. So this is the condition to get maximum power across the load. Okay. So substituting RL equals to the Rs in equation 2. Okay. So in equation 2, so PL equals to the VS square plus Rs plus RL whole square into RL, right? Okay, substituting here to get the maximum power, PL maximum. Okay, that is equals to the VS square. Here RL becomes Rs. Okay, so whole divided by Rs plus RL equals to the Rs whole square. Okay, so here finally PL maximum, so that is equals to the VS square divided by Rs whole divided by, so Rs plus Rs 2 Rs whole square. Okay, so VS square into Rs divided by whole square 4 Rs square, right? Okay, Rs cancelled. Okay, remaining PL maximum equals to the VS square divided by 4 Rs. Okay. So in case 1, circuit contains DC voltage source and variable resistance and source resistance Rs, right? Here the power equation, the maximum power equation, that is equals to the VS square divided by 4 Rs. Okay. Here in this figure, so here power delivered from the source, that is input power, right? So it will deliver some input power, the input power from the source, so that is equals to here P in power delivered from the voltage source Vs, that is equals to the, here voltage is Vs and current from this source is, that is IL, right? So Vs into IL. So substitute IL value here. Okay, so P in equals to the Vs into IL. Substituting IL value here, the Vs into, so IL, the Vs divided by Rs plus RL, right? Okay, so here Vs square divided by Rs plus RL. Applying MPT here. So in MPT condition, the maximum power transfer condition, so P in MPT so that is equals to the, so RL equals to the Rs, right, in MPT. So Vs square divided by Rs plus RL value in tagontira Rs, right? So Vs square divided by 2 Rs. Okay, so this is as equation 3. Okay, so consider this one as equation 4. Okay, here I will find efficiency here. The efficiency, so that is equals to the output power, so power across the load divided by the input power, the power delivered from the load, the maximum power delivered from the load. Okay, so into 100, right? Okay, the efficiency equals to the, so power across the load maximum power, that is Vs square divided by 4 Rs, right? The whole divided by the Vs square divided by 2 Rs. Okay, Vs get cancelled. Here Rs cancelled. So what you get? into 100, right? Okay, so here efficiency becomes, so 2 divided by 4, right? 2 divided by 4 into 100. 1 divided by 2 into 100, that is equals to the 50%. I already told that. So MPT will provide 50% efficiency, right? Okay, thank you.